Welcome, ladies and gentlemen, to your PN3 notes. So pre-calc 3 notes, I'm going to put that up in the top left-hand corner. I'm going to try anyway. There we go. Pre-calc notes number 3. And today we are going to talk about inverses, everything that you can think about when you think about inverse functions. That is what we are going to focus on today. The definition of an inverse relationship is written there. It says the ordered pair AB is a relation if and only if the ordered pair BA is in the inverse relation. And while that is kind of general theoretically written, I'm just going to kind of make sure you hear the nuts and bolts, which is that if your function has AB as a point, then the inverse function, if it is an inverse, will have, and I'm going to write inverse function, will have the point BA. And that is really what inverse functions are all about, is that you're swapping the x and y's. When you look at the graph, it's reflecting across the line y equals x. Everything is about just switching your x and y coordinates. There's a very fast way to determine whether a function's inverse is going to be a function, and that is using the horizontal line test right here. And it's very, very nice and straightforward, just like the vertical line test. All you're doing is seeing if when you draw a horizontal line, if it intersects at more than one point, and if it does, then that function's inverse itself is not a function. So let me try to say that again, because that's a lot of words. So, or you know what I think I'm going to do? How about we just go right down right here. I'm going to call this number 1, this number 2, this number 3, and this number 4. And I think rather than just talk about that horizontal line test, let's actually back up, and with each one of these graphs, let's determine whether they themselves are a function. So the first thing that we do is to do the vertical line test to determine whether these graphs are functions. So looking at number 1, which is a hyperbola, if you do a vertical line test, it is in fact a function at no point on that graph, even though it does get very, very close to the asymptotes, infinitely close in fact, it still will only hit once, or not at all, but never, never more than once. So letter A here is a function. So let's see what else over here is a function. Number 2, well, anywhere there pretty much kind of fails that vertical line test, so number 2 is not a function. Number 3, not a function because it hits more than 2 spots. And number 4, interesting graph, right? It also is a function, just like number 1. And again, I realize that some of these lines are curves are very, very steep, but they are still a curve, and it will only hit once with the vertical line test, even though it is steep. So number 1 and number 4 are the functions. Now I'm going to erase my vertical line tests, or try to just erase the vertical line test here. Okay. Now let's talk about the horizontal line test, and I'm going to just shake it up and use a different color. So the horizontal line test determines whether or not the graph's inverse is a function. So like for instance number 1, we already know it's a function, looking at it and doing the vertical line test. If we do a horizontal line test, here it only hits once, here it only hits once, here it would, actually the x-axis it wouldn't hit at all because it is an asymptote, but that's okay. So notice the horizontal line test does pass, which means then that the relation has an inverse that's a function. So number 1, if we actually found the inverse of that, it would be a function. I'm going to erase all these horizontal lines so you can see the function. So because it is a function and its inverse is a function, we call that one-to-one, and it is on the second page, but I'm just letting you know that number 1 here is kind of special because it's one-to-one, and what that means is that it's a function and its inverse is a function. Number 2, if you do a horizontal line test, doomp, 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 it passes. So while number 2 is not a function itself, its inverse is a function. Number 3, yeah, the whole ellipse thing isn't working for me. It's not a function, and its inverse is not a function. So if you do a horizontal line test, although that's not really horizontal, but you get the drift, it's going to hit more than once here. So right there, and then I do understand over here it doesn't hit at all, but really what happens is if at any time it hits more than once, bam, it's not a function. This fails right here, so this is also inverse is not a function. So again, number 3 and number 4, while number 4 was originally a function, its inverse would not be a function. So that is how, without doing any other work, how you can decide whether or not a relation or a graph has an inverse that's a function or not a function. Kind of like that. Okay, so now I have no idea how to switch it to the other side. That's really interesting. I didn't think about that. Let me see if I can do this. Okay, so here we have, it says on the back, a function whose inverse is a function has a graph that passes through both the horizontal and vertical line tests. Such a function is 1-to-1. So I kind of said that earlier with a little bit more or a little less verbiage. But anyway, so a function is 1-to-1 since every x is paired with a unique y and every y is paired with a unique x. Very exclusive, right? So graphically, that is how you determine whether or not you have a function, and if you find the inverse, if that inverse is a function without actually having to do any of the graphing, which is lovely. So again, all you have to do is look at the original graph and use that to determine whether or not the inverse is a function. Now, a good question would be, how algebraically can you find a function? I know you were thinking that. So example number 2 here talks about that, and I do want to mention, first of all, that when you see this notation, f of -1, that is really not f of -1, even though that is what I always tend to say. It really stands for the inverse of f, or f inverse. So if I do say f of -1, it's a bad habit, and I should say the inverse of f. Anyway, so all you do, there's really 2 steps, and they are very, very straightforward. So step 1 is that you take the function f of x, which in this case is x plus 1, and you just switch, like we said earlier, all you're doing is switch your x and y. So you flip them over. So here's what I'm talking about. First of all, I'm not going to use f of x because that's just sloppy. So I'm just going to go y equals x over x plus 1. All I'm doing is writing the function just in terms of y instead of with that f of x notation, the function notation. Now I'm going to switch my x's for y's and y's for x's. So instead of y over here, I'm going to say x equals y over y plus 1. And then all you have to do for step 2, which actually tends to be the part that students get kind of jumbled up on depending on their algebra skills, is you need then to solve for y and then use notation. Solve I've come here for y and use function notation, so the inverse, and then put it in that form. Okay, so let's do that. So I'm looking at this x equals y over y plus 1, and I am simply going to first multiply both sides by y plus 1. If you don't know what I'm talking about, another way to think about it is put x over 1 and then cross multiply, setting up as a proportion. So you end up with x times y plus 1 equals y. So again, I'm cross multiplying if you want to think of it that way, or I'm just multiplying both sides of the equation by y plus 1 to get rid of the fraction. I'm going to distribute my x through, so I have x times y plus x equals y, and the reason I'm doing that again is I have to get all the y's together to solve for y. So now I can move this plus x over, and I can bring the y over to the left side, so I can move the x to the right and the y to the left. So I have x y minus y equals negative x. Now, this is why we reviewed factoring at the beginning of the year here. You see how we have y's in both terms. So I'm going to pull out the GCF, which is the y. I end up with x minus 1 left over equals negative x. To solve for y, I divide both sides by x minus 1. So I end up with y equals negative x over x minus 1. Now, if you leave it there, it's okay. It's not like the worst thing ever, but I do want to say this, that if you were to multiply the numerator and denominator by negative 1, so let me say this again, if you multiply the numerator and denominator by negative 1, it makes it look cleaner, nicer. So if you do that, negative 1 times negative x is x. Negative 1 times x minus 1 is just going to be 1 minus x. And I remember as a student thinking, what in the world? But if you do it long-handed, you know, negative x plus 1, then you could shift it around. So either one of these is right, but I'm just letting you know the second one is cleaner and more right, if you want to think of it that way. Anyway, so now let's write it as in inverse notation. So we have the inverse of the function in terms of x is equal to x over 1 minus x. And this, ladies and gents, is the inverse of example number 2. And that is really the nuts and bolts of it. Lots of just algebra. Okay, so let me just think what I wanted to. There was something I was going to say about this. Oh, down below in example 4, we're going to talk a lot about the domain and range, but I do want you to note what would not make sense for x, and obviously in the original function, negative 1 doesn't make sense for x because you can't have 0 in the denominator, and for the new function, it's not negative 1, but it's 1, so you can't have 1. Now that's just a coincidence that they're opposites of each other, but I do want to show you in example number 4 how when you switch your x's and y's, you're really switching all your x's, all your x points to your y points and y points to your x points, so really the domain and range just switches. So I can tell you right away that the range of the original f of x function was actually going to be where y is defined, we're everywhere except for 1. And now you notice that that is the domain of the inverse function. So the x and y's switch, and so do the domain and range. Just kind of throwing that out there so that when I don't shock you when I do example number 4. Okay, example number 3. We have two functions here. We have an f of x function, we have a g of x function. There's a quick check to determine whether they're inverses of each other, and all you have to do is do a composite. So let me show you what I'm talking about. So if I find f of g of x, and when we find that, if it equals x, when you simplify, that means that they are inverses as long as the other composition also is x. Let me just show you by example here. So we have f of g of x. Let's test this out. I'm going to put g of x here in for f of x. So I have, and I'm glad you guys have your note guide in front of you because my screen is very hard to read. I apologize for that. So I'm putting the cubed root of x minus 1 in for x, and that, you know what, just because of space here, let me just erase that little thing right there. So I'm going to have, I'm going to put the cubed root of x minus 1 in for x, and we know that's cubed plus 1. When we simplify that, first of all, we know that the cubed root cube undoes each other, so you end up with x minus 1 plus 1, and notice that that simplifies to x. That is a check. That's a go, a green go here. So now these two, f of x and g of x, are inverses of each other if this also, works for the g f of x. Okay, so let's just check this out really quick. So I'm going to put f of x in for g of x. So I have the cubed root, and I'm going to squish it in here. So I have x cubed minus 1, no, plus 1, minus 1. Plus 1, minus 1. So this here is the f of x function. I'm substituting that in for the x in the g of x function. And when I simplify it, I have x cubed, because plus 1 minus 1 obviously is 0. And cubed root undoes each other. And you end up with x. So what does this mean? This means that f of x and g of x are in fact inverses of each other. So, and I really wish I had more space here, so sorry about this, but f of x and g of x are inverses. Maybe it was better when I was typing, huh? So they are inverses of each other. And what that means is if you graph of f of x and graph g of x, they are identical functions except for the x and y coordinates are just flipped. So you can look at the table and verify what I'm saying. We'll be doing that in class next time we meet. So the very last example here that we're going to do, it says show that f of x is equal to square root of x plus 3, or excuse me, show that that function has an inverse function, and find a rule that f negative x, find a rule for the inverse of x. Sorry, you guys. State any restrictions on the domain of f and also the inverse of f. So let me just start by saying that the square root of 3's graph, and I think I might, I was going to erase some of the stuff on the top just so I have room, but I'm going to just sketch what the graph of the square root of x plus 3 looks like. This right here is negative 3, and this is going to start here, and it's going to do this little thing. There's your square root of negative 3. Looking at it, doing the vertical line test, yes, it's a function. The horizontal line test, yes, that's a function. The domain of f of x is going to be, and I'll write this up here, hopefully we don't get things confused here, and you write it down where it belongs, but, and I'll do it in interval notation here. I was going to kind of avoid that, but the domain is going to be starting at negative 3, so it's closed bracket, and we're going to go to positive infinity. The range, if you look at that graph, is going to start at 0, and it's actually equal to 0, starting at 0, and you're going positive. How do I know this? Well, I'm looking at the graph. You can look at your table. Domain is very easy to see algebraically. You can't have 0 under the denominator, or excuse me, negative numbers under the denominator. Yeah, and all the things we've been talking about for the last week. Okay, so now I do want to say this. If I graph in y equals x, which is the reflection line for inverses, and I know you talked about that probably quite a bit last year, that means that the inverse is going to reflect across that. So if I want to actually graph the, this is going to be ugly, but just kind of bear with me here. It's going to look, all I'm doing is I'm reflecting across the axis. I always go where it hits first, and then I kind of close my eyes and graph. Ugh. Okay, so the green line, or excuse me, not a line, the green curve is the inverse, where the blue curve is the original function. Now, let's find it algebraically. And all we have to do, again, is switch the x and y's. You gotta love that. So I'm going to do that down here. I'm going to do it right away because of space. So I'm going to go x equals the square root of y plus 3. I square root both sides of the equation to get rid of the square root. So I have x squared equals y plus 3. And then when I subtract 3 from both sides to solve for y, I'll end up with the function f of negative 1x, so that again is the inverse of f. And what do we have? I'm going to subtract 3, so we have x squared minus 3. Now, you guys know that that's a parabola. I'm looking at it, you know that's a parabola, it's a quadratic, and it starts, the vertex is at negative 3 on the y-axis, but notice the green graph that I drew is not the entire parabola. And the reason for that is that the original function did have restrictions, and those restrictions get inherited by the inverse function. So remember I said the domain and range right here for the original function will be the domain and range for the inverse function, but just reverse. So instead of the domain being -3 to infinity, it's going to be 0 to infinity. And if you look at the graph, and that's where I'm looking at, I'm like, oh my gosh, I really graphed it badly. So I'm going to have to tweak this so you guys do a better job than I did. Oh, look at that. You guys, make sure you tell me how horrible this video is when you do it. Oh my gosh. No, not. So, there we go. And here it is. Ooh. Yeah. And that is much better. So the domain is going to start here at x is equal to 0 and go to positive infinity. So I'm trying to prove it to you, but I will say this. If you look at the square root function and just switch the x and y coordinate points, graph those, you'll get a much better graph than what I just did there. So the domain for the inverse here is going to be starting at 0 and going to positive infinity. Okay, so folks, really hopefully what you got out of this is when you're talking about inverses, you are switching your x and y coordinates. It reflects across the line y equals x for obvious reasons, because that shows y equals x and vice versa. We talked a little bit about the domain. We're going to practice that a lot in class because that's a little weird. And also tested whether two functions are inverses by doing example number 3, by doing the composites. Okay, well, any questions you have, we'll address them tomorrow in class. Thank you for tuning in.